Thank you very much. First of all, I just want to give two warnings. One is that, unfortunately, I came down with a very bad cold in the last 48 hours, so I apologize for that, because this microphone's going to pick up all the wheezing. And also, when I showed this presentation to my kids, they said, "Dad, that some of those videos are a little bit freaky." So I give you that warning in advance. When Dr. Jayas asked me to do this, he sort of said, "Well, Peter, just tell them a little bit about your research, what you're doing, spend a little bit of time on that, but very quickly go into this issue of the future, issues that research will illuminate and feed into." So I was really amused when they came to me and gave me this title, Dial D for Diagnosis, because I suspect many of you in the audience have never seen a rotary phone like this. So just as a nod, in a way, to at the very least, being contemporary and to the future, I've decided to change the title somewhat and go for Text T for treatment. Now, as Dr. Jayas said, my area is really, or at least in terms of applicable work, is in the area of heart disease, heart attack, response to injury, trying to protect the heart from injury and perhaps even repair it. With that in mind, just by show of hands, how many people in the audience have actually made a heart? Can you just raise your hand if you've ever made a heart? Well, that's really interesting, because it must be the way I'm asking a question, because everybody has made a heart. I know that's true because once upon a time you were all a single cell. Well, technically, of course, you had a half-cell existence, half of your genetic information coming from your mother and half of your genetic information coming from your father. But that's the subject of a completely different talk, so we won't go into that. Interestingly, this is the first cell, and if you can see these two fried egg-like objects, those actually represent the genetic information from the mother and the father just before they come together and get reorganized in a way that will ultimately result in a gene set, DNA gene set, that is unique to that individual. You may be similar to your mother, you may be similar to your father, but you're not identical. You have a unique gene set. But that isn't really what really got me into this area of research. It's what happened next. I mean, this really had a profound effect on me. Because what happened is this cell decided to divide. And what was remarkable is before this cell could divide, all of that genetic information had to be duplicated. All those A's and T's, C's and G's that everybody's always going on about. All of it had to duplicate before one cell could become two, each one with the identical genetic complement of the other. That's 6 billion base pairs of DNA. And the A's and T's and C's and G's all have to be in the right place. 2 cells then become 4, 4 cells 8, 8, 16 and so on. Each time before that division occurs, those A's and T's have to be put in the right place. Never have you worked with such precision and accuracy. I'm glad I don't actually feel as though I was in charge of this particular process. I would have messed up royally. I'd put an A where a T should have gone, or a C where a G should have gone. But nonetheless, that memory, that knowledge is contained within those cells. But if you take that out to its logical extension, then what I should be facing and what you should be looking at is a ball of identical cells. And clearly that's not the case, well, at least for most of us. Something else happened. At some point, some of these cells decided to grow off in a different direction, becoming our arms, our legs, and others growing off to become the organs of our body. And one of the very first is the heart, such that we end up with a human being. So the difference between this and this isn't really the genetic complement, the genes. It really is how these genes are used, gene regulation. In other words, the same genes are in your heart as are in your liver. But a liver cell and a heart cell are different because of the subpopulation of genes that are used in one cell type versus the other. Regulation has occurred. So that's really the first idea I want to get across to you, is that one cell has the knowledge and the memory when jogged through the regulation of gene expression to generate the whole complex organism. But it does more than that. It does more than contribute to our birth, if you like. It contributes to the events in our life, things like puberty, etc. And this is the first of those freaky videos. There's no sound, actually. It's much better with sound. Oh, there you go. There's puberty, the voice breaking. Now things start to go downhill. There's the arthritis. There's the heart attack. Life is short. And clearly there's a genetic component. We all know that. We constantly are being told there's a genetic component to things. And that brings about the idea that some people have good genes. We hear that, oh, good genes. But can we rely on it? We could ask Mr. Zhang Zhuqing. Here he is celebrating his 100th birthday, proudly boasting the fact that he has taken on about a ton of nicotine during his lifetime. I believe he was smoking at the age of 12 and proudly smoked every day of his life and was drinking accordingly. Sort of high-risk behavior. But nonetheless, he lived to be 100. But what's interesting there is that we all essentially have the same sort of genes. I mean, if we were to analyze and compare you, as I said, we'd all be very, very similar. So the difference really isn't totally to do with genes. Yes, there are certain gene mutations and things like that that lead to diseases, but a lot of it is involved in what I'm going to talk about, which is regulation. So I've drawn this analogy with the books. It's not a perfect one, but it does convey the idea. If we think about the genome, the A's, T's, and C's and G's as the alphabet, then the words that we can create with those letters are the genes. And they are contained within our dictionary. That's our source of words that we can use. And ultimately, from that, we can generate a whole series of books. Arguably, the books are similar, but not the same. Some are more entertaining than others, some are longer than others, and other things. So what is it that you put between these words and the book? And I would argue that one of the most important, back to school, is grammar. And grammar really is the regulation. Grammar is the rules by which you put these words together to make sentences, such that these sentences give direction and sense to what's being said. And punctuation as well. Punctuation gives emphasis, changing the whole meaning of a sentence. So this is a very, very important part of the process, and that's one of the things that my laboratory studies. And at its simplest, and I really am oversimplifying this, one of the key things is whether our genome is open or closed. In other words, whether a gene that's there is open and available to be expressed, or closed and now unable to be expressed. And the first thing to realize when you're thinking about that is that DNA, or the substance that makes up the genes, does not exist as naked substance in the cell. It's complex with protein into something we call chromatin that constitutes the chromosomes. At its simplest, it has this sort of beads on a string-like structure. And these beads on a string essentially represent an open conformation. In other words, the genes there are open and you can get expression initiated. If it gets folded up much more than that, this is a sort of higher order folding fiber, if you like, then that process of starting a gene to be expressed doesn't happen. So this process is very, very important. It's important because in the end, moving from one form to the other, it will determine if, where, and when a gene is expressed. So I'm just going to give you one example, and I don't worry about the details per se, but just conceptually. In this particular case, I'm talking about something called histone acetylation. The bottom line here, though, is that these beads, in this beads on a string-like structure, can either hug each other, like this, and become very, very close, in which case they form a structure like this and things don't happen, or the arms can be opened out, and as such, genes can be expressed. And through modification to these little tails that these individual beads have, you can favor one direction or the other. And in this particular case, it's acetylation. If you have acetylation of these little tails, you favor an open structure. If you deacetylate the opposite, then you favor a closed structure. So you've got this dynamic process going on. So if you wanted to open the gene, for example, what you'd really want to do is interfere with this acetylation, the ability to deacetylate, favouring acetylation and an open structure. Okay, sounds all very technical and wonderful that you can do that in your lab, and these are some of the graduate students working, PhD students in the lab working in this area. But it is practical. The example I'd like to give you, and it's a fairly recent one, is I'm sure you're all familiar with the immune system. At some point early in your life, a decision has to be made as to what is self, what is you. And there is a system of regulatory T cells using a bank of genes that goes out and essentially, to all intents and purposes, tags every part of you as self, your heart, your liver, etc. Everything as self. But then that shuts down. And the reason that shuts down is that subsequent to that, if you're invaded, you get a bacterial infection or something like that, you don't want that process at play. You want to be able to recognize this as a foreign agent so you can protect yourself for it. It's wonderful. There is one time, though, where you might want to change that. And recently, and it appeared in the paper, less than 2 weeks ago, was some work done by Dr. Hancock from Children's Hospital in Philadelphia. And what he decided to do was this. He said, okay, if you're going to get an organ transplant, it would be really good, rather than have to go on lifelong immunosuppressant therapy after you receive the transplant, if we could, just before you get that organ, open up again those genes that tag things as self. So the idea then is to reopen that whole network so that when you get that foreign organ, it's now tagged as, oh, you're part of us. You let that thing close up again, and then you return to a situation you had before. And that's what he did. Now, why is this relevant to what I've just been saying? Well, because the approach that he took was to actually block this deacetylation process. So in other words, what he did was he focused on these regulatory T cells, opened up the genes, gave them an opportunity to re-tag things as self, allowed them to close up, and then went through the organ transplant and had a positive outcome. So although this is being done in animal models, one can see going forward that this is going to be very powerful as an approach in order to facilitate organ transplants. More importantly, it's just one example of understanding the grammar, the punctuation, etc. In this particular case, we were targeting on one particular cell type and genes in general. But the more we know about the punctuation and the grammar concerned with each individual gene, the more the chance we have to actually target those genes in a corrective gene therapy way. In terms of our own research, our particular cell type of interest is the stem cell. Now, I'm not talking about fetal stem cells, and I'm not even talking about those that come out of the testis. Here I'm talking about perhaps what's better termed as the adult stem cell or progenitor cells. These are cells that you currently have in your body. If you watch any doctor or health-related shows, you almost certainly have run into bone marrow cell transplants. And bone marrow cells are examples of these sorts of adult stem cells. They have the capacity, maybe not like that very first cell that we came from, but not far off, to be converted with the right triggers into a number of different cell types. So it's of interest if these cells are in fact wandering around the body looking for opportunities to assist when an injury occurs. This is some work done by a graduate student in my lab, Sarah Jimenez, and what you're seeing here is a section through a heart. This green, pale green staining is actually the muscle cells of the heart. These little blue dots represent the genetic material, the genes in the nuclei. In this lower panel, what Sarah's done is isolated bone marrow cells and injected it into the heart. She's done that just to see if it was there, whether she could detect those cells apart from anything that was in the heart. And if she could, she would see a distinctive, very bright green staining, which you have to see using a confocal microscope and at much higher power. But these intense little green specks betray the presence of these stem cells. So this is a very artificial situation. We've taken a heart, a normal heart, and injected them with bone marrow cells. But what she's done then is to go on, and I just focus your attention on this panel here, to look whether in a heart which has been subjected to a heart attack situation, whether there are in fact these stem cells floating around. And if you look carefully, you will find. So the trick now is that we know these cells are there. We know they're being recruited there, if you like, in the event of a heart attack. The goal now is to amplify or enhance that response to get a better regenerative response in the event of a heart attack. So what Sarah is doing, she's working with cell biologist Dr. Elisabeth Kardami at the Institute of Cardiovascular Sciences and a cardiac surgeon, Dr. Devinder Jassal, to essentially improve the environment in which these cells are present. In a sense, it's through growth factor cocktails and exercise. If you want to translate that into simple language, it's about supplying them with the right foods and giving them plenty of exercise. It's a theme I'll come back to a little later. So just to summarize that in general, in terms of our regenerative medicine approach, the trick is to identify the cells that you particularly want to work with. In this case, we're working with these progenitor cells. And we want to be able to identify them, perhaps so that we can pull them out of even the heart to actually amplify them, and then put them back in. So we want to be able to come up with as many markers as we can. The other thing we want to do is work on this grammar and punctuation. We want to know what DNA sequences and proteins are required to regulate all the genes. What are the rules of this process? And the reason for that, of course, is that during development, things can go wrong. And there's a chance with this process that we can go back, correct things, and get it right the second time. So if we know how to switch on and off genes, we can actually make corrections, corrective gene therapy. Ultimately, though, we also need to understand the optimal environment to stimulate growth. And this is really where the regenerative medicine comes in. And as I said to you, one of the things we're working on in our lab is to use a series of what we call growth factor cocktails. And the idea really is to send these cells off to the equivalent of Hawaii with a nice glass of wine. Now, it's one thing to make cells, and we're talking about using these cells that exist in our own system, but that's a little bit distant away from actually creating artificial organs. Nonetheless, recent breakthroughs in this area suggest that this is also possible. Again, you may have seen in the newspaper, it was well publicized at the beginning of the year, from a group in Minnesota, Doris Taylor's group, where essentially she took a dead heart, washed out all of the cells, leaving just the, if you like, the sac, the matrix of which the heart was encased in, and then repopulated it with baby cells. And miraculously, the thing grew back into something which was a beating organ. So the possibility of generating organs for organ transplant from your own cells is now a real possibility as we look forward into the future. So we're working on all of those ingredients that will make those cells grow in a controllable way. And what this sort of approach provides is a template, a framework in which to grow those organs. Obviously that we already have some artificial blood. It's not great, but those things will improve. And so the future, this is still a ways off, but the idea of having these organs for us is a real possibility in the next 20, 25 years, maybe earlier. But sometimes biology needs some help. Sometimes you can't do everything with biology, and I'm just going to give one example, and I hope I'm not bouncing into somebody else's presentation, but I call it biology and technology. And the example I would give is of eyesight. Now, in many cases, not in all, blindness, in the case of blindness, there is no problem with the optic nerve, that part at the back of the eye that then feeds a signal from the retina to the brain. It's intact. The problem is the signal coming into the eye and reaching the retina. So, you don't have to be a genius to think about some of the developments that we've had recently that may play into this. Digital cameras, amazing advances. Even within your phone now, you can get a 5 megapixel camera. And I'm not talking about movies necessarily, but snapshots. The idea of being able to receive an image, a complex image in real time, that then could be fed to a processor, a computer, if you like. Now, 15 years ago, that would have been something like this. But now it could easily be something that you could carry on your chest and would be getting smaller and smaller and more powerful. So the idea of being able to interpret complex images, then the next step would be simply to take that information and figure out how to map that or translate that into signals that you would stimulate the optic nerve with to create an image. So you've got a biological problem, that is how to stimulate the optic nerve in a way that the brain can then interpret into an image, and then processing power to enable you to convert straight digital imagery into that. So again, I would predict in the future we can look at quite sophisticated methods for dealing with some kinds of blindness. And yes, I think it is possible, given that in the end, most of this will be dictated by the input that comes in through the camera here. The capacity to have the sort of things that we associate with the $6 million man, or more recently the bionic woman, various capabilities with that are actually in the realms of possibility. But where do you go to get able or healthy? If I said to you, if you wanted to get healthy doing all these things, in the past it was easy, you'd say I'd go to the hospital. The trouble is that hospitals are fast becoming a place for sickness, and I mean that in that double-edged way. We see more and more the argument for face masks. We see these bacterial lotions all over the place, everywhere we go, and I've got a cold at the moment. I feel obliged to wash my hands continually. And how many of us can say that we've been in a waiting room and are looking around thinking, my gosh, I came in sick, but I might be much sicker by the time I leave. So this is a real problem. And I've got just a little clip from a popular TV show that I think identifies the problem.
Well, if the staff can't wash their hands, it's no wonder an infection is spread. Hey, tie clip.
Sorry?
We have an epidemic in this hospital, and your tie is becoming a petri dish. Put on a tie clip or take the damn thing off.
And this is actually based on a real study. This is a study, and I remember it back from 2004, which found that the ties that clinicians, when they were walking around wards and things, were in fact a major source, a significant source, I wouldn't say major, but a significant source of transferring various infectious agents around the hospital. And I was asked actually to give a presentation around this time by a group at the University of Manitoba. And somewhat half-jokingly at that talk, I proposed the following: radical tie surgery to deal with this. This is a before and after image of what I was proposing. Unfortunately, when you put this into practice, there are unfortunate side effects. But nonetheless, if you, going back to this popular TV show, you see I was somewhat ahead of my time.
Oh, I warned you.
So there you are, radical tie surgery in practice. Now, although I'm making light of this, it really portrays quite a serious issue, and that is the one of superbugs. I'm sure you're familiar with this. And whether you think of this in terms of the overuse of antibiotics, antibiotics in our foodstuffs, etc., we do face some real threats. A very common one is MRSA, methicillin-resistant staph. Now, interestingly, that really isn't technically a superbug in the sense that we have an antibiotic that we can still use against this. But nonetheless, when you look at the statistics, and I just took this off the Public Health Agency of Canada website, and the stats are a little old, but you can see a growing trend of this rather nasty bug in our hospitals. While in Canada we sort of claim as though we're getting this under control, I think it's fair to say that in the United States they've pretty much thrown up their hands on this one. So it really is a frightening situation. And of course there really are superbugs. The VRE, the vancomycin-resistant enterococci, is a real superbug. And this is going to be a growing issue, particularly with an aging population. Whether you just think in terms of urinary tract infections, etc., there's a real pool here of potential to create problems. So I'm predicting in a way two things. One, which is the obvious, that we are desperately looking to come up with antibacterial agents, more antibiotics. And we have some top people at the University of Manitoba, George Zanel, Michael Mulvey, working in this area. But I think that there's another consequence, and I think it's that we will become more and more looking for not going to the hospitals or places where we could potentially infect ourselves. And you get a sense of the possibilities around this when you think about telehealth, which is with us now. So we already have devices where we can listen to our chest at a distance, where we can do x-rays at a distance, where we can do sonography, ultrasound at a distance. And companies, this one recently from Quebec, is already offering diagnosis at a distance for a price. So if you follow that trend, then I would argue that what you're going to be looking at is more and more assessment devices in the public, and perhaps, I think, in the not too far distant future, within your homes, that you will be looking to have these assessment devices there. So I'm not advocating that we'll barcode everybody like Hitman here, but it's not science fiction. Just recently in Ontario, they announced an investment of many millions of dollars to set up a barcode system, or a system to do an analysis from a drop of blood of many hundreds of infectious agents. So you can very quickly see how these assessments may grow, and once this market's there, grow beyond just infectious agents, but just normal developmental processes. It won't be very long before you're all carrying cards, or would have the ability to carry a card with your complete genome printout on it. Currently, there are companies for about $1,000 willing to give you a pretty good size number of markers for your genome right now. So the idea of this information being contained within a card that you will carry around or use to upload and be detected somewhere else, whether it's a hospital or a clinic, etc., is in the not too distant future. And I could go on about that. The one that I find the most exciting, though, in a way, is what we call whole body imaging. This is a whole body image from the 1990s. I think you'd be hard pushed to say what that is. You might think it's a skull. You can see the eye sockets here. This is something from 2000 of the same era. And I think you can see a dramatic difference in improvement in the scanning and detection, so that you can see that this is in the thorax area. So going forward, the capacity to get better and better imaging is going to happen. So what are the advantages to this? Well, just think about it for the moment. I'll just give you two. If you could get up in the morning, walk into a shower-like device and do a scan, and then scan yourself a year later, and this information was put into a computer and analyzed for potential differences, you could very quickly diagnose potential problems well ahead of the problem itself. So that's one, and maybe I'll come back to that. The other thing is, your doctor, if you're going in for surgery, if you can have a whole body scan, your surgeon, before you even enter or even makes a first cut, can have essentially planned out your surgery down to each cut, predicting what he needs to do or she needs to do before you're even there. So even in the context of actual surgery, you have the capacity for reducing the intervention. And what sort of surgery are we talking about? I think, well, again, we're talking about computer-assisted surgery, and there's already 3 types of that available, but we'll see future developments there too. Supervisory controlled systems. Essentially, this is where the robot, to all intents and purposes, is doing it with minimal intervention from the surgeon. Telesurgical, often favored by individuals, because although the surgeon, a robot is doing the surgery, the surgeon is the person doing the manipulations, and their motions are translated through devices to do the surgery. And there's the shared control system, which is just a combination of the both. So I've got another one of these freaky short clips, and just to show. Now this is an example of a telesurgical system. It's actually the Da Vinci system. This is where the surgeon would sit. This is the bit that would actually work on you, usually through 3 holes, and you're going to see the size of one of those holes. And actually the surgery that's been going on is an actual valve replacement. Now this would normally involve cracking open the chest to do the surgery. In this particular case, the surgery is done through 3 small holes. I can tell you that part of the recovery time, or the majority of the recovery time, is to recover from that chest opening. This sort of surgery, you'd be going home in weeks. If you had the cracking open the chest, we're talking months. So that's the sort of hole size that we're talking. That'd be one of the holes. It may be 3 like that. Here's the surgeon, and the translation of the movements. I'm not sure if I've missed that. Now, this surgeon, although might be in the same room, there's no requirement in the same room. They might not even be in the same building. Actually, not even in the same country. Of course, there'd have to be some remarkable changes to our wireless networking, because I wouldn't want to have this and it suddenly lose control. But the idea then that you could have... Okay, now the good news is that our next generation of surgeons are already in training. Do you have any sound? There are a number of motion-sensitive game systems, and only a couple of weeks ago, because I wanted to include it in this presentation, I had a go at one of them, this Trauma Center New Blood. It's actually very interesting. I've got a very crude little image of this. This is a game in which you can do some interesting surgery. Sorry about the quality, but there's all sorts of inputs that you get, and the stitch work wasn't particularly good there, but that was cool. This is on easy, mind you, and you can, you're reassembling bones, etc. But actually, to be perfectly honest, this wasn't me doing it. This was a kid from up the street who I invited in to have a go with this. This is his first attempt, so it wasn't so bad. So you may already have budding surgeons working in your dens or in your basements already practicing for the future. Okay for the future. All these wonderful things going forward. What about for us people now? One of the things that I did mention earlier is that our lab also works in the area of exercise. And one of the amazing things that does seem to be the case is that the body seems to be able to respond in a very positive way to exercise. We believe those stem cells respond to that exercise. We believe that even the protection from the heart attack can, in a very biochemical way, be enhanced to actually optimize on an individual basis. So again, going forward, instead of, and we've all seen it, if I said to you, how do you assess your exercise and how it's going, you usually get images like this, one of two. It's either this or this. And you take into account body mass index and etc., etc. What we were trying to do here is to really get this down to where individually you might do a saliva test, urine test or whatever, and get a very personal and accurate readout of what exercise is best for you, whether it's before a heart attack or after a heart attack. But in this study that came out last year, almost a year ago I suppose, there was some really remarkable data that suggest actual reversing of aging. The markers they used are very meaningful, but literally they were actually rejuvenating cells. So maybe there is something in this. So now, as promised, looking into the crystal ball, if I could just say a few things. Yes, I do think there will be longer and healthier lives. I think home-based health and wellness assessment devices will be growing. I think there'll be a real market for these. I believe that portable coded personal information from you is going to be a scan away and will be very important. It makes logical sense if we're going to get diagnosis at a distance and not be going into hospitals just when we're sick. If we want to know in advance. And quite clearly, if we do know in advance with a lot of disorders, we know that there's advantages. And I'll just go down here, eradication of some cancers. Again, we know with some cancers, if we can detect them before they become neoplastic, if we detect the pre-neoplastic lesion, we can wipe it out. We don't have to develop the full cancer. So again, assessment devices that allow this in advance will lead to some of those cancers going. Pre-planned and often less invasive surgeries require shorter recovery times. Again, whether that's through the robotics or whether it's through the scanning again, whole body scanning. Corrective gene therapy. This has been a bit of a hiccup. When corrective gene therapy came out, people were putting potential replacement genes into viruses, infecting people, and there were all sorts of consequences. Yes, there might be a positive one, but there were all sorts of negative ones. What we're starting to see, if you combine this with regenerative medicine, stem cells and things like that, is that what you plan to do is correct in a particular cell type and then put that back in rather than trying to do whole body things. So I think there's going to be a real renaissance on this and some real positive things going forward. Again, with stem cells, we're learning an enormous amount of information about stem cells that relate directly to cancers. There's a complete paradigm shift. I'm quite happy to talk to people about that, but I don't have time to go into that now. Regeneration and repair of damaged tissues and organs. I think that is the breakthroughs, again, that relate to stem cells, relate to to also the combination with technology mean that I think there are real possibilities in terms of organ replacement, but also in injuries that we haven't been able to do very much for so far, such as spinal cord injuries. So I think that that is likely to happen in the future. Lastly, and perhaps probably the most controversial, is this idea of one-tier healthcare in Canada. This will continually be a debate. I'm not coming down one way or the other on that. I'm just putting that there as a comparison, because where I do think that we're likely to see a change is in the possibility of what I am almost calling two-tier health assessment will be accepted. And that is, if you can afford these devices and put them in your home to protect yourself, it's like information. You will be in a position to take better advantage of the healthcare system. In a way, and you may think this is trivial, if I asked you how many people here buy organic vegetables, fruits and vegetables, by show of hands. Anybody who makes a point of doing that? There's a few hands. And presumably part of this is that you recognize, or you've accepted the information out there of the potential health benefits of using these, of taking in this nutrition as opposed to others where there might be pesticides and things. However, there's a premium with that. You pay extra money for that. So I could ask the same question about how many of you are members of a gym or something like that for exercise. In other words, there's already this separation, and this would just be another example of that. But clearly, this will have a major impact. So I'd just like to end there with thanks. First of all, I'd like to thank Dr. Giles for inviting me to speak to you today, Mr. Guy Levesque and the National Science and Engineering Research Council, as well as the other sponsors for this event. All those behind the scenes, I can see some of them up there, Sean and Kim. I particularly want to thank members of my laboratory. I don't really do very much. They do all the work, as do my collaborators, and the University of Manitoba for providing the resources for us to do it. All of you really, through tax dollars, providing money via the federal agencies, the Canadian Institutes of Health Research that fund the research that I have in my lab. And last of all, thank you, the audience, for taking the time out here to listen to me today. Thank you very much.